So I will speak about Hardy spaces. So I will be working with Hardy spaces on the torus. So T is the unit circle, and we are on the d-dimensional torus, and we equip it with the Har measure, which is just a normalized Lebesgue measure. You have the product measure of TD. And then HP of TD is the closure of the analytic polynomials in LP on the torus. And H infinity is just a space of analytic functions, bounded analytic functions in the d-dimensional multi-disk. Well, I want to include d equals infinity, so I am lying a little bit to you when I say that these are just bounded analytic functions in d infinity, because you need some, there are some technical challenges there. But for that, it is perhaps better to just, well, you should probably read the left of these when you read the slides. So then alternatively, we can define these spaces in terms of Fourier coefficients. So f is in LP of I can point with the arrow. Yeah, so f is in LP of TD. Such a function is in HP if the Fourier coefficients of all entries that are not where the multi-index with the entries alpha 1 up to alpha d are one of them is negative. In that case, we require it to be 0. So that's the usual definition of Hardy spaces in terms of Fourier coefficients. Okay, so then so we're seeing 2 slides at a time. I don't know, this has never happened to me before. So, well, I'm really bad. In spite of my background as an engineer, I am really bad with these things. I'm sorry. Okay, so then you have HP on the torus, and then there is another Hardy space which I call curly HP, which is really HP of T infinity in disguise. By which I mean, maybe I can remove that. That helped. Yeah. So then we are looking at Dirichlet series, and we take the, we are here. So we take the closure of all Dirichlet polynomials, finite sums like this, a and n to the minus s, with respect to what is usually called the Besikowicz norm. So we take the mean, the LP mean of our function or the Dirichlet polynomial on the imaginary axis. So IT, we are on the imaginary axis, and we let the t go to infinity. Okay, so this defines a norm on the Dirichlet polynomials, and we take the closure of such polynomials with respect to this norm. And in the case when P is infinite, we declare that curly H infinity consists of Dirichlet series that represent bounded analytic functions in the someone is saying something to me now, or I said that these spaces of Dirichlet series, when the dimension is infinite, is just the previously defined HP spaces in disguise, and the way to see that is to set up a map from Dirichlet series to power series in infinitely many variables, where you take Pj to the minus s. Pj is the nth, the jth prime. You send that to the variable zj. Then, of course, by the fundamental theorem of arithmetic, you formally get from a Dirichlet series to a power series in infinitely many variables. But you have much more. You have actually an isometric isomorphism of curly HP onto the Hardy space on the infinite dimensional torus. I like to think of this as you may think of HP of T infinity and curly HP. Well, I told you they are different representations of the same object. And you may think of it much in the same way as you may represent the zeta function, the Riemann zeta function, as respectively an Euler product and the Dirichlet series. One of the representations stress the multiplicative point of view, and the other stress the additive point of view, the additive structure of the integers. I think this is a good way to think of these different ways of representing the same object. And the second point I want to make is that we have, of course, a profound understanding of the operator and function theory in the one-dimensional case when D is 1. And in comparison, our comprehension of the higher dimensional case, D larger than 1, is, I would say, much more rudimentary. You might say that this talk is about certain points of view that can be useful for increasing our understanding of the higher dimensional case. Okay, so why should we study contractive inequalities? By contractive inequalities, I mean in inequalities where the constant involved is 1. Okay, so norm inequalities with a constant 1. And it really begins, I think, with the work of Frederick Bayard in 2001, and later by Helson in 2006. Both recognized that certain contractive inequalities involving norms of HP or TD can be particularly useful when the objects in question, like the norms and or an underlying operator, lift in a multiplicative way from 1 or sometimes few variables to several or infinitely many variables. And this has led me to look more systematically at various contractive inequalities for the spaces that I just introduced above. So what I will do in this talk is to speak about, I will try to make a summary of recent work that I have done with several collaborators. So I will report from one paper written jointly with Sergei Konyagin, Hervé Kefelec, and Eros Saxman, and several papers written with Ole Fredrik Breivik and Joachim Ortega Seda. So before I start speaking about this, I would like to explain what we can gain from such a study. And one, at least surprising point to me, is that this infinite, I mean, the infinite dimensional viewpoint, then I keep in mind that we go all the way to D equals infinity. We go all the way to the spaces curly HP. The infinite dimensional viewpoint surprisingly yields new perspective even on the in the situation that we believe we know all about, namely the case D equals 1. And I will give you an example of this phenomenon. The second thing is that there are interesting phenomena appearing in the transition from finite to infinite dimension. And this is being revealed, I would say, when we look at these contractive inequalities. And then there is a surprise, and it certainly was a surprise to us when we studied it, is that even interesting phenomena may appear in the transition from low via intermediate to high dimension. And the example that we will look at is a study of so-called idempotent Fourier multipliers. And finally, we will see that we can even shed some light on the Banach space geometry of HP. of TD, and we introduce a notion, the notion of Hilbert points, which is some kind of extension of inner functions. I realize that probably I'm trying to say too much. I hope that I can give you a glimpse, at least, of these things, and I will be very sketchy with technical details, and of course proofs. I will not say basically anything about. And then let me start. So I will. So you see here to the left 4 points that I want to make, and I will correspondingly mention 4 results / problems related to these 4 points. So let's begin with the first, where we see something interesting even in dimension 1 from the infinite dimensional point of view. Okay, and this is what I call Hardy-Littlewood inequalities. I use the word Hardy-Littlewood inequalities because Hardy and Littlewood studied lots of such inequalities that we will see, and but it's fair to say that they of course they didn't really care so much about the constant involved, and we really care because in our case we are interested in the case when the constant is 1. Okay, so I'm now telling you about work done by Helsen in 2006. So Helsen did the following. He started with a classical work by Kalemann, who proved the following inequality for Hardy spaces on the circle. Okay, so you have an analytic function with Taylor series like this, n, a, n, z to the n. Then we have the following bound for these weighted, there is a, yeah, it's correct, yes, it's correct. For the square sum of the coefficient with this weight, with constant 1. Okay, so what this says in terms of Bergman space is that to the left you have the square of the Bergman space norm of the function, and to the right you have the square of the H1 norm of the function. And what Helsen did with this inequality was to lift it to the infinite dimensional, to an infinite dimensional inequality. So he made a clever multiplicative iteration of Minkowski's inequality, and got from 1 dimension to infinite dimension. Now, on the right-hand side, you still have an H1 norm. What I have done now is to let this F be a Dirichlet series. So in order to get a power series, I use this Bohr lift. But just think of this as the H1 norm of your function. On the left-hand side, the weight will be more complicated, but it's easy to understand how you get from this to this. D of n is the number of divisors of the positive integer n. Okay. You can see how you can see that if you have only 1 prime involved in your power series in infinitely many variables, so that it reduces to 1 variable, then of course the number of divisors of p to the n is n plus 1, and you get such a contribution from all the primes, and altogether you get the so-called divisor function here. So this is of course an inequality with an obvious number theoretic appeal. Helsen didn't use it for number theoretic purposes. He used it to prove that the Hardy's theorem for multiplicative Hankel forms, that means Hankel forms on the infinite dimensional torus, is valid when the symbol is in the Hilbert-Schmidt class. I will not go through the technicalities here. If you know what these things are, you may appreciate it, and otherwise you shouldn't care too much about it. So this is, but so this has, as I said, an obvious number theoretic appeal, and such inequalities have been used to study the so-called pseudo-moments of the Riemann zeta function. So there are also number theoretic applications of inequalities like this. And then comes a very natural question, which is to ask what happens if you instead go to HP. So instead of having the H1 norm on the right-hand side, you have HP. And then you see that this divisor function that you had before should be replaced by a fractional divisor function, which are, well, actually here I am in the one-dimensional situation. So here, of course, these weights here are the binomial coefficients. Okay, so you have C sub alpha, the binomial coefficient you see here, and alpha is 2 over P. So this is what it should be. Okay, and it was proved by Bourbia in 1987 that when 1 over P is a positive integer, this inequality is indeed true. You can do it, you can prove it by just working with the coefficients. But there is strong numerical evidence that it holds for all P. And now we come to the number theoretic part. You can then do the same as Helton did. You can iterate, and you will get yourself a similar number theoretic inequality when you go to infinite dimension. Here, the coefficients, this fractional divisor function will be the coefficients of the Dirichlet series of the power z to the alpha, zeta to the alpha, the Riemann zeta function to the power alpha of S. So this is a very nice and interesting inequality, but we don't know if it is true. Well, we believe strongly that it is true because we have strong numerical evidence, but we haven't been able to prove it. We have been able to prove certain weaker things, but we haven't been able to prove that. So what I did some years ago with this group of authors was to reformulate the problem, and we ended up with a problem which might, perhaps from my point of view, is even more appealing, because it is a statement about reproducing kernels. So going from this inequality with Taylor coefficients, working with basically the well, I don't want to go through the details, but you can get from that to a statement about reproducing kernels in H2 of T. Something very basic, something very that I thought I knew everything about, but it turns out that I don't. So the statement is the following: the reproducing kernels solve the problem of maximizing the hyperbolic area in the Poincare disk model of this set. Okay, so you take your function in H2, you put on a weight which corresponds to the weight of the normalized point evaluation in the space, and you fix some lambda lying between 0 and 1. If lambda is 1, the reproducing kernels will maximize the value of the point evaluation at the point. So then this will you will have equality in only one point. But when lambda is strictly between 0 and 1, you may get a set of positive measure in a positive hyperbolic measure. And the claim here is that the reproducing kernels solve the problem of maximizing this hyperbolic area. I find this a fascinating problem because it gives you a very it says something stronger than what you're used to see about reproducing kernels, about their localization in phase space, if you like. It would establish a strong geometric localization property of reproducing kernels. There is again strong numerical evidence that this is true, but we lack a proof. We lack a proof. So this ends the first part, where I wanted to tell you that starting from this infinite dimensional situation that we had, we wanted to get to these inequalities on the infinite dimensional torus. We need to solve a problem back in the disk, and back in the disk we discover a very nice problem about reproducing kernels that we are still unable to prove, but it's a challenge to the audience, of course, to do it. I'm spending far too much time, so I will have to rush. Sorry for that. Okay, so next is a problem about Riesz projection. What is Riesz projection? Well, it is, we have a Fourier series, f in L1 of TD, well, a Fourier series of a function in L1 of TD, and we do orthogonal projection onto H2. It means that we just restrict to the non-negative frequencies like this, right? And as an operator on L2 of TD, it has, of course, norm 1. Now, I'm a bit, I'm not completely happy with this way of presenting the slides, but I cannot do it better. I'm sorry for that. Okay,
so you can read it.
If we instead view the Riesz projection as an operator on LP for P between 1 and infinity, then there is a theorem by Hollenbeck and Verbitsky which tells us that, well, the norm is of course not 1 anymore. It is precisely this number. So sine pi over P is what you get in dimension 1. And this lifts multiplicatively to several variables. So we get the one-dimensional estimate to the power D. And then if we go all the way to infinity, then we see that Riesz projection is bounded only when P is 2, because this number goes to infinity when D goes to infinity. So this is the only case when Riesz projection makes sense as an operator from LP to LP. So the conclusion is that we see nothing interesting when we go from 1 to infinite dimension. So what should we do? Well, one possible thing to do is to look at Riesz projection as going from some LQ space to an LP space. So what I will do is, in particular, to specialize to the case when we start in L infinity and go to some LP. And of course, we have this bound. This is trivial since infinity, since we go from L infinity, where the norm is larger, to LP. There is an object here, which we call the critical exponent of Riesz projection, which is the largest, or the sup, over the P's, such that the norm is 1 when we go from infinity to P, okay? This, of course, is well defined. Well, actually, you can check that this function is continuous, and you also check that. Well, of course, for in the case when P is 2, we have norm 1. So this is well defined, and for some P between 2 and infinity, it happens that this may start growing. And it turns out that when you are in dimension 1, the critical exponent is precisely 4. There's a neat argument showing that. And you can also show that it will be smaller when in higher dimensions. So you get a bound like this. So this is what something I did with Jordi Marzo some 10 years ago. And we were stuck at the time. We wanted to know more. We wanted to know what happens with PD when we go to infinity. And it turns out that finally we were able to solve this in the paper I mentioned before with Konyagin, Kepfelek, and Saxman, we were able to show that actually this critical exponent tends to 2 when d goes to infinity. And since I'm running out of time, I will probably just say one more thing about this. And that is that you see a very striking contrast with one dimension when you go from to infinite dimension here. So the analytic dual of H1 is the Riesz projection of L infinity, right? Because L infinity is a dual of L1, so it has to be a Riesz projection of L infinity. So in one dimension, that would be just a space of analytic BMO functions. But what we see here when you are in infinite dimension is that because of the result that we have to the left, the dual space of H1 of T infinity is not contained in any of the spaces HP of T infinity for any P larger than 2. In one dimension, in contrast, you have that BMO A is contained in the intersection of all these HP spaces. I put here an indication of the proof, but I think it's better that I skip it because otherwise I wouldn't be able to say, come to the third point I wanted, or the third result that I wanted to mention. But this ends this first example of something interesting happening when we go from 1 to infinite dimension. So now we come to the third issue, which is idempotent Fourier multipliers. So what are they? Well, we start now in LP, right? So we are in LP. We represent P is larger than or equal to 1, so that we have a Fourier series. We represent our function in terms of the Fourier series. We have the frequencies. Alpha will be lattice points, ZD, and then we have a set lambda of frequencies. And the multiplier is the operator that just restricts the summation to those frequencies lying in lambda. Okay, so it's a subset of the d-dimensional integer lattice. This is the Fourier multiplier that we're interested in. We started to look at this because there are a number of interesting such multipliers that appear in applications that are, for various reasons, are contractive. So one is an inequality that goes back to the work of Bohr, and Bohr referred to an F. Wiener who found this inequality. So what is the inequality? Well, we are in dimension 1, and then if lambda is an arithmetic progression, then in fact we have contractivity for all P. This was proved and used by Bohr. It's a simple trick to prove. And it has been used several times by others. Then another interesting such inequality, which is contractive, so when lambda has norm 1, is when you restrict to the M homogeneous terms of a power series. So you see, so lambda here, you see, you fix an M, and you require the so now I'm dealing with positive, I'm dealing with non-negative frequencies. Okay, so that I have already gone to HP. So then when you are dealing with M homogeneous terms, which means that you require this, Then you also have contractive inequalities, and this inequality has been used by many people. That it has been used in operator theory, in number theory, and in function theory. It's a very useful and nice inequality to have. So what we wanted to understand is what's behind this. I mean, what are there other such inequalities I mean, which are exactly the lambdas that give you contractivity, which are the Fourier idempotent Fourier multipliers that act contractively on HP. So it's natural, before we go to HP, to start with LP. That is presumably an easier problem. So let's start there, and we call lambda a contractive projection set for LP if this Fourier multiplier extends to a contraction on LP. Okay, then I follow Rudin, and Rudin uses the following terminology. So we say that lambda is a coset in ZD. I mean, remember ZD is the integer lattice, or sometimes it's called an affine lattice if it is a coset of a subgroup of ZD plus. So it just means that it is a subgroup shifted by some fixed vector. And it's a result that wasn't written out explicitly by any of these two people, Ando and Rudin, but this follows from their work that in LP, lambda is a contractive projection set if and only if lambda is a coset in ZT. You can go back and check for yourself that, of course, what we had before, these are indeed cosets, the case of arithmetic projections in dimension 1 and M-homogeneous polynomials in higher dimensions. Okay, so I added here something which is for us more of a curiosity, but I think it's worth mentioning that, of course, you may ask, okay, but what about just boundedness? Now I'm speaking about contractive Fourier multipliers, but what about bounded Fourier multipliers? And it turns out that there is a very striking situation, because in L1, we can indeed describe the bounded Fourier multipliers. And this is the result of many of work of many people. It starts with Helsen in dimension 1, Rudin in higher dimensions, and later Cohen for compact abelian groups. And we may relate this result of Ando and Rudin to that by saying that we have boundedness in L1 if and only if we have a finite union. Lambda is a finite union of cosets of ZD. But for other P, it is a difficult open problem to describe the sets lambda that yield bounded operators P lambda on LP. So contractive Fourier multipliers represent an easier problem than bounded Fourier multipliers. Okay, so now we go to HP. Right. So far we discussed LP. Now we go to HP, and we use the same terminology. A subset of now we have the natural numbers here, or actually n naught, because we have to include 0. Okay, this is what Helsen in his work refers to as the narrow cone, and somehow what we're doing gives some kind of justification for that that terminology of Helsen. So this lattice, this part of the integer lattice with entries that are non-negative, I will refer to as the narrow cone. Okay, so a subset lambda of this narrow cone is a contractive projection set for HP if F lambda extends to a contraction on HP. Okay. It is, of course, an immediate consequence of the result that we had for LP, that if lambda is a coset in ZD, then the intersection of lambda with the narrow cone is a contractive projection set for HP, since HP is a subset of LP. And the question is, are there other contractive projection sets for HP? This turns out to be a very interesting problem, and it turns out that the dimension of the affine span of lambda, this set lambda lies in it spans the vectors that you between the points in lambda, they span a certain span a subspace of RD, and the dimension of this space plays a role. So we call that the dimension of the lattice, or sorry, of the set of frequencies, lambda, and it plays a non-trivial role. So I have to make a somewhat more complicated definition here. So we have K lying between 1 and D, which you may think of as the dimension of the set of frequencies. We then say that HP of TD enjoys the contractive restriction property of dimension K if every K-dimensional contractive projection set for HP of TD is of the form given by the Andor-Rudin theorem. So in other words, this is the situation where when nothing interesting happens, so to speak. We get everything from Andor-Rudin. That is basically what this definition says. But it turns out the next theorem tells us that there is an interesting situation here. So this is the theorem I want to say something about now. So let me try to read it slowly for you. So there are 3 parts. Part A, you should think of as low dimension. Part B is intermediate dimension, and part C is high dimension. So when you are in low dimension, meaning precisely when the dimension is 2, or the affine the dimension, the affine this K is 1, then there is nothing else. Then so then HP enjoys the contractive restriction property of dimension K if and only if P is different from 2. Of course, P equals 2, I should have mentioned that before, is not interesting, because then all contractive projection sets, all sets of frequencies are contractive projection sets. So P equals 2 is not interesting. But for all other P's, we are covered by the Andor-Rudin theorem. So in some sense, nothing new or interesting happens in low dimension. In intermediate dimension, which means precisely when D is equal to K is equal to 3, or the dimension is larger than or equal to 3 and K is equal to 2, then we have that nothing happens, interesting new happens when P is different from 2 and 4. So 4 now in dimension, when P is 4, there are other such sets that are not covered by the Andor-Rudin theorem. And then when we go to higher dimensions, in fact, the situation is completely different, because then we have that this contractive projection restriction property of dimension K holds if and only if P is not an even integers. So then, let's say, funny things happen for all even integers. Is a rather is some contrast between these 3 cases of low dimension, nothing new happens. Intermediate dimension, something new happens when P is 4, and high dimension when funny things happen for all non-negative, for all even integers. Well, I should be able to finish, so I will not say, well, on this page, there is something about what the proof is about. It's a geometric problem, which you could say has to do, to solve this problem. Well, there are actually two components. One is that it is to a large degree a question about orthogonality and in LP spaces. So the reason that something happens, well, that 2 and 4 appear here, is that in some sense you could say that orthogonality in L4 is somehow closest to orthogonality in L2 if you compare with all different LP spaces. It's a vague statement, but roughly speaking, that's how one may think of it. So this is one side of it. It is a question about LP orthogonality. The other is that you are led to a very interesting geometric problem, an extension problem. So to prove this theorem, you have to understand this extension problem, and this extension problem is very much about this narrowness that I mentioned about you know, this set N naught D. I'm using, and I find this very good, this notion that Helson used, the narrow cone. It becomes more and more narrow when the dimension grows. That is sort of the philosophy behind. Okay, I'm sorry for being so vague, but I should try to reach the end of the talk before my time is out. So it is a geometric extension problem that you need to solve to prove this this theorem. So that was the third thing, but there is a nice thing coming out of the proof, which is a very exotic linear operator. You get out of this a very exotic linear operator. What is that? Well, what we can do using one of the examples in the proof of the previous theorem is the following. There exists a linear operator Tn that is densely defined on HP of T infinity for every P between 1 and infinity, and that extends to a bounded operator on HP of T infinity if and only if P is 2, 4, and so on up to 2n plus 1. So you see, if you ever thought of interpolating here, of course, you would be in trouble. And this is a result that exemplifies, I would say, quite strikingly, the impossibility of interpolating between Hardy spaces on the infinite dimensional torus. This was has been studied in depth in a recent paper by Bayar and Mastillo. So you have a very concrete operator here, which has a very exotic behavior, something that you wouldn't expect to see. We have an upper bound for the p's involved here, 2 times n plus 1. It would be interesting to know if you can go all the way that you could actually get to a bounded operator that, well, to an operator that is bounded on HP if and only if p is just an even integer without this upper here we have only finitely many. I'm asking if you can do it for all even integers. I don't know, but I can say that this would solve a problem that has troubled me for at least 20 years. And if we could find such an operator, that would give some evidence to well, there is a problem in the theory of Hardy spaces of Dirichlet series, which is an innocent-looking thing. So you take a Dirichlet polynomial capital F, you take the integral on a finite segment on the half line, And you ask yourself, when will this integral be bounded by the corresponding norm integral, right? So you remember this was how we defined the norm for curly HP for polynomials. And this inequality is known to be true when P is an even integer. It is not very hard. When P is between 0 and 2, it was proved by Adam Harper quite recently, a very remarkable result, that it fails. It fails when P is less than 2. Now, it remains an open problem what happens for P in the intermediate intervals between the even integers. We don't know. But we know that if this fails, then we would have this exotic operator that I asked for on the previous slide. Okay, I see that my time is actually out now. I have 2 more slides about what we call.
If you want, I can give you still 5 minutes.
Yeah, okay, I will. I won't take much. I mean, I don't want to take too much time. But now this was again an example of an interesting phenomenon happening when you go from in the transition to infinitely many variables. So now we come to the 4th point I wanted to make about, so to speak, about interesting phenomena happening. Well, that you see something in the Banach space geometry. So now we change our setup and fix a function instead of a set of frequencies. So we say then that a non-trivial function phi in HP of TD is a Hilbert point if we have this norm inequality for all f in HP such that f and phi are orthogonal in the usual sense. Okay, so this is just usual L2 orthogonality. I know that I'm cheating a bit, but I have there are some technicalities that you can read about in the parentheses. So you see, what do we have? We have a situation which is what we're used to if P is equal to 2, and I want this to hold for all P. So you could say that what this kind of point, this is a very special kind of point in your Banach space, and you could say that around this point, the Banach space locally looks like a Hardy space. Sorry, like a Hilbert space, because it has exactly the same behavior as you would expect your Hilbert space to have, and you can actually make more sense of it. You can. I mean, there are various ways of making this more precise. You can look at these balls. So I have P BP is this ball with this radius, and then phi is a Hilbert point in HP if and only if the supporting hyperplane T2 to B2 contains the point phi coincides with the supporting hyperplane TP to BP that contains phi in this precise sense that you have this equality between these two sets. I need to take the intersection to make them appear as the same sets. So what I'm just trying to say is that Hilbert points are points around which your Banach space looks like a Hilbert space. Okay. We wrote a paper about this, and we found some interesting things. Well, there is one way to characterize them in terms of this non-linear projection operator. So these are precisely the Hilbert points are precisely the solutions to this equation. And then if you are in dimension 1, This is just a new word for inner functions. So a function phi is a Hilbert point in HP of D if and only if phi is a non-zero multiple of an inner function. But when we go to higher dimensions, new things appear. So for instance, a one-dimensional homogeneous polynomial is a Hilbert point in HP when P is between 2 and infinity, if and only if the non-zero coefficients all have the same modulus. We believe this is the case for all P, but we cannot prove it. And actually, this discussion of Hilbert points also lead to a new proof of the Khinchin inequalities in a certain range of the powers involved for so-called Steinhaus variables. And well, the third point, the last point here is that there are Hilbert points beyond the one homogeneous polynomials. And I don't know how plentiful the universe of Hilbert points are. I believe it would be very interesting to find out more about Hilbert points in higher dimensions. They appear as very interesting objects, and who knows, they could also have a role to play in operator theory. Okay, I'm sorry for spending too much time. I go to my last talk, which is just a very brief summary. I started by saying that I'm interested in contractive inequalities because they are useful. There are various applications where it's really useful to have contractive inequalities. But what I've been trying to say is that at the same time, I think that contractive inequalities can be viewed as a tool to unravel some of the mysteries of these spaces, which we know too little about. Thank you very much for your attention.